Assalamu alaikum. Can you hear my voice? Can you hear my voice? Okay. Is there any question? Is there any question about the past lectures? Repeat the association rules. We will talk about them, Nur Adnan. We will talk about association rules again in this in this chapter. But before that, we should find frequent patterns. Firstly, we will find frequent patterns, then we'll talk about association rules. Okay. As we talked in the last lectures, we need to know and find frequent items. But how? Here, in this chapter, we will talk about some methods, some well-known methods to find frequent item sets and frequent sets. The first one is Apriori, and then we will talk about F-gross and equilat 2. Okay. One of the first algorithm to find and calculate the frequent item sets in a data set is Apriori. This algorithm uses a simple principle. This principle is this: if there is any item set which is infrequent, if there is any item set which is infrequent, it means that my item set cannot cover minimum support and minimum confidence. Its support count and confidence is less than the defined threshold. Okay, so if there is any item set which is infrequent, its superset should not be generated and tested. Why? Because the supersets would be infrequent. If an item set is infrequent, then its superset would be infrequent. So we can remove them easily. We can forget the superset easily because we know that those supersets are infrequent. This is the basic principle in Apriori algorithm. So we can prune the rest of sets. Just we need to find an infrequent item set. Then we can remove the rest of candidates. But how this algorithm works? The method works in this manner. Firstly, we should scan the data set or database to find the frequent item sets with only one item. Firstly, we find all frequent item sets with only one item. After that, in a loop, we can generate a new candidate with k plus 1 items. We can generate new candidate, new candidate item sets with k plus 1 item from item sets with length k. We are generating we are generating a new item set with k plus 1 item from other item sets with k items. But according to the principle, those item sets with k item must be frequent. Those items with k items must be frequent. So we can continue to generate k plus 1 candidates until reaching to an item set with k item which is infrequent. When I found an item set, an infrequent item set with k items, according to the principle, I should remove the rest. I should forget this generation process. Okay. Then after generating a k plus 1 candidate item set, I should test it to find that is the candidate frequent or no. We will do this loop multiple times, generating new candidates and testing them until all candidates be infrequent. In other words, the algorithm will be terminated when no frequent or candidate set can be generated. We have not enough sets to create or to generate a new frequent set. At that time, we can terminate the algorithm. For example, we have a data set here in the left side with 4 transactions. The first record contains items A, C, and D. The second one contains B, C, E. The third one A, B, C, E, and in the fourth one B, E. And the minimum support count is 2. Okay, so we have 5 different items, A, B, C, D, and E. We scan the dataset to find their support. We scan the dataset to find its supports. Sorry for interrupting. Okay, so I have these data sets with mean support equals to 2, mean support of 2. In the first scan, I have 5 different items. So in the first step, I should create item sets with only one item, A, B, C, D, and E. And I'm calculating their support counts. For example, here in the data set, I have 2 records consist of A. I have 3 records including B, 3 records including C, 1 record including D, and 3 records including E. Okay. Okay. So just in the first step, just I scan and count number of A, B, C, D, and E in the dataset. I will complete this table here. Here I can see that D, the support count of D is 1, which is less than the minimum support threshold. My minimum support threshold is 2, and D is the support of D is 1. So it's less than the threshold. I should remove D. So the table will be edited in this manner. The result is this table. Only A item sets with A, B, C, and D would be remain as frequent one item sets. Then I can combine A and B together, A and C, A and E, B and C, B and E, and C and E. I can combine these one item sets together 2 by 2. So I can find 6 different candidate combinations. A, B, A, C, A, E, B, C, B, E, and C combinations. These 6 sets are my candidate. Again, I should find their supports. So in the second scan, in the second round, I'm counting the support counts for 2 item sets. As you can see here in the middle of this slide, the item set A and B just repeated 1 times. So the support count of A and B is 1. Also, for A and E, the support count is 1, 2. So A and B and A and E are not frequent. And I can remove them from the table. So I have 4 different 2 item sets that they are frequent. Now I have find new candidates with 3 items. Here I have A, B, C, and E. So I can create A, B, C, for example, ACE, ABE, and BCE. But if I try to create for example, ABC, if I try to create a set A, B, and C, I need subset A and B, A and C, and B and C. One more time. To create or generate subset A, B, C, subset with 3 items A, B, C, I should have subsets A and B, A and C, and B and C. And as I look in the L2 table here, in this table, I cannot see A and B. In L2 table, I cannot see subset A and B. A and B was not frequent. We removed it in the past step. We removed it in the past step. So item set A, B, and C cannot be a candidate. A, B, and C cannot be a candidate. because A and B is infrequent. So I cannot create A subset A and B, superset A and B and C. I can do this method. I can apply this method for the rest of supersets. For example, what about A, B, and E? Unfortunately, I have some problems with my internet link. Okay, I'm repeating again. Here in L2, I have A, B, C, and E items. So to create a superset with 3 items, maybe one candidate is A, B, and C. Maybe. But as I look here, A, B, and C has 3 subsets: A and B, A and C, and B and C. And as I see in table L2, A and B was removed because it was infrequent. So according to the principle, to the basic principle of Apriori, A, B, and C cannot be a candidate because A and B is infrequent. So A and B and C must be infrequent, would be infrequent. I can do something like this for A and, for example, B and E. Or A, C, and E. In all of these supersets, we have an infrequent subset. So I cannot generate those supersets with 3 items. Only for B and C and E, for B, C, and E, you can see in L2 we have 3 different subsets. We can see it's 3 different subsets: B and B, C, B, E, and C. All of these subsets are frequent. So according to the algorithm, I can create the superset B, C, and E. And I can calculate It's super count, support count. Its support count is 2. When we create the L3 table, we can see that we cannot continue our way to generate more new supersets. So after creating L3 table, the algorithm will be finished. This is a basic. This is a simple example about the way that Apriori works. Why support is 2? Here you can see in the second record B and C and E. Also in the third record we can see B, C and E again. So in 2 oh sorry. So we can see that B, C, E are repeated 2 times in all records. B, C, and E are repeated 2 times, so its support is 2. B and C and E are repeated together in 2 different records. So here, using Apriori algorithm, we can see that item sets A, B, C, E, A and C, B and C, B and E, C and E, and B and C and E are frequent. These frequent item sets are presented in tables L1, L2, and L3. This is the pseudocode of Apriori algorithm. You can read it and work on this algorithm by yourself. And okay, I can pass this one. Okay. This algorithm, the Apriori, has a big problem. Why? After creating candidates, for each candidate, I should count support for each candidate. It means that in each round, at least I should scan the data set 1 times, at least. So for a big data set with multiple items, I can see too many possible candidates, so I have to scan the data sets multiple times. It's too time consuming because as we talked in the first lectures in this course, today we have large and huge data sets. We are talking about big data today. So calculating the support counts using this simple method as Apriori do is not easy. And sometimes it's impossible. But how we can improve this method? How we can improve this method? One method is using hash trees to store candidate items. Maybe we can in this hash tree we can put candidates in a tree. The leaf nodes in this tree is a list of different items and their counts, and in the interior nodes contains the hash table, and we can use some subset functions to calculate the counts. So the best way to reduce this overhead, reducing the overhead of counting in Apriori, is using a tree, a hash tree. Okay, I will pass these slides because it's not important for me. You can read them by yourself. Okay. Also, we can make other improvements on Apriori method because this method suffers from different challenges. One of them is multiple scans, multiple database scan. The other challenge is a huge number of candidates. And the third challenge, the third major challenge is the workload to find the support counts for those candidates. So we can work on three different general ideas to reduce the overhead of Apriori. The first idea is reducing number of passes or number of scans, number of database scans. The second idea is shrinking number of candidates, reducing the total number of candidates. And the third idea is facilitating the support count process. For example, in VLDB 95 conference, an improved version of Apriori is presented. In this presented algorithm, the authors firstly divides the data set into some partitions. Firstly, they divide the complete data set into some partitions. And in each partition, they calculate the support, local support, to find that, okay, is this partition frequent, yes or no? So in the first scan, they just calculate the support count for each partition. And then in the second scan, they calculate global support, and they found global frequent patterns. But in this way, they just focus on the partitions, partitions that consist frequent patterns. Those partitions that their supports is higher than a threshold. So this method only needs 2 scans, nothing more. For example, another method, DHP method, is presented in Sigmod in 95 conference. This method tries to reduce number of candidates using a hash table algorithm. Also, another paper in VLD 96, Tavinon presents a new method for large data sets. This method focus on sampling. This method tries to get some samples from the original data set, because the original data set was big, so we couldn't work with those large data sets. So firstly, the algorithm tries to select some samples to create a smaller data set, and then the algorithm tries to find frequent items in that smaller data set. Here the algorithm just tests the border of closure of frequent patterns, just those patterns that have higher chance to be frequent. In this way, the method could miss some steps. And it's a fast method. Just by scanning a database, it could find missing frequent patterns. Another method presented in SIGWIT 97 dataset was dynamic item, was DIC, reduced number of scans. Here in the left side, left button, you can find the citation of this paper. In this method, the others try to reduce total number of scans to find frequent patterns. Okay, so Apriori has some problems. In VECA, if you go to the association rule, let me check. In VECA, you can find Apriori. Just simply, you can go to the is British first search. It means I should generate K item sets, calculate their support counts, and after that, I should work on K plus 1 item sets. This is the British first search. I should come. You have problems with the voice? Okay. Can we go to prepare for the exam? Why? It's just a simple quiz with only 5 multiple choice questions. You only need 5 minutes to answer. It's simple, don't worry. You can start the exam after after this class. Okay, so using the British first strategy, British first search strategy, and need to create lots of candidates, generate lots of candidates, and test them makes lots of performance issue for Apriori. In the FP growth method, the others propose to use a depth first search strategy, and they try to avoid generating candidate explicitly. Instead of that, the major philosophy behind the path FP growth is that line patterns are growing from short ones, but just using some local frequent items. For example, if I have ABC in all transactions, then I can check the ABC regarding to the whole data set or whole database. So I can, for example, check the D as a local frequent item with ABC. D is a local frequent item set. I can check D with ABC. I know ABC is frequent, so just simply I am adding D to this pattern. And then just I need to check is ABCD frequent, yes or no. Here, let me show that how FP groups works, just using a simple example. Suppose that we have a data set like this. This data set has 5 different records and a list of different about items, sold items, in this way. Firstly, according to this table or this data set, firstly, we should find and calculate support count for each item separately from the rest of items. Each items. Here we have items A, B, C, D, E, F, J, F, J, M, N, O, P, S, K, and something like that. Okay. So from this table, I can find all subsets with one item. Also, in this example, we know that the mean support is 3. So simply we can remove those items with support count less than 3. The result is this. The result is presented in a header table. We can see that F has the highest frequency or support. Its support is 4. C, the support counters of C is 4, and A, B, M, and P are repeated 3 times. So their support is 3. We remove the rest of items because our mean support is 3. Okay, we remove the rest of items. Then, after creating this header table, we can change or bound items in this way, something like this indeed here. Firstly, we can remove infrequent items from the list. For example, I is infrequent, so it's removed. For example, G is infrequent, so we removed it. Okay, firstly we remove infrequent items, and then we sort items in a descending manner. F has the highest support, so we put it in the first place, then C, after that A, M, and P. We will do this in all of those records. For all of those records, we will do the same method, removing infrequent items and then sorting items in descending manner. Okay. After doing this, we will start to create a tree, an FP tree. The root of FP tree is an empty set. Then and after okay, why empty? Because it's root of 3. After that, I'm starting from top of this tree. Let me check something. Okay, here. To create this tree, we should create a conditional pattern. According to this list, this header table. This header table is presents frequent items, and I see that it's in descending manner, sorted in descending manner. So I can check, for example, if has the highest frequency here, if together with other items, for example, F with C, F with B, with A, and others. Okay. Firstly, I'm selecting F with C according to their support counts or frequency. So firstly, I check F with C. I can see that in the data set, we can see F, a combination of F and C 3 times. So in 3 times, we can see F and C together. So firstly, I'm starting from the most frequent item and try to combine it with different items with lower number of frequency. So I'm starting from C combined with F. And as I checked, its frequency is 3. So in the 3, I'm writing F and its child is 3. 3 is repeated 3 times and F is repeated 3. And after that, I can see, for example, add A to F and C. I know that F and C is frequent and A is frequent too. So I can I create a combination F A with F and C? As I checked, their combination is 3. The frequency of their combination is 3. So here, I'm adding a new child for C. Its content is A. A is repeated with C and F for 3 times. I can do this with B. B is repeated with C, with F, and with F, C, and A. I know F is frequent, C is frequent. Here I found that FC is frequent too. And also I found that F, C, and A is frequent too. So I'm trying to find combinations between B and F B and C, and B and FC A. Here I can find that B and F is repeated 1 times. So I'm adding a child to F. This is B and F. A child to C. Look at this, B and C here. I'm adding a new child to the root. We have a combination of C and B. F is not presented here. But as I can see, F and C, B and C is repeated only 1 times. So here we can see this. C is repeated 1 times with B. And F, C, and A here in this pass. F, C, and A. In the next step, I can see M is the 5th frequent item in my list. So I can make combinations with those items, M with FCA and FCBA. And you can here in the tree, you can find those ways, FCAM or FCABM. FCAM and FCABM. So to create the tree, we need to find some conditional patterns. These conditional patterns follow this strategy. Find a frequent pattern and then add another item which is frequent too. Adding a frequent item to well-known to noun frequent sets. And then you can put them in this tree. Nuradon asked me why the root is empty. You can find the reason. Because FCA and the rest of this this part of this subtree all of the left subtree is started with F, but in the right subtree we cannot see F. In the right subtree we can see just C, B, and P. So we're putting an empty root here. To create a tree. Otherwise, I should create multiple trees. Also, you can see some pointers here with dashed line. Each pointer is connected to each frequent items. To each frequent item. Here, for example, I can see I have 3 different B's. One of those B is repeated in the pass from F, C, A, and B. One of those B is visited from the pass from F to B, and one of them can be visited from the pass from C to B. But here, for example, A can be visited from this path, F, C, and A. And now I can see that F, C, and A is repeated 3 times because A is 3. So support or frequency of A is 3 in this table, in this tree. Just simply I can start from the root and follow the passes one by one to find the frequent patterns. For example, CB is not frequent. CBP is not frequent because their frequency is less than the minimum one. Don't worry, Nur Adnan. You have enough time. I think about that. I put enough time for you to do your exam. Don't worry. I will finish the class soon, and then you can go and do your exam. So simply by creating conditional pattern bases, you can find different items where those items and test that those items are frequent or no, or infrequent. Just you need to find just you need to look at the support count in each node. Just simply. Here in F growth, you don't need to pass multiple scans. Just simply you need to create a header table and arrange that table, and after that you need to scan again the data set to create the tree. Nothing more. So it's much easier than Apriori. So preserve complete information for infrequent pattern, and never break a line pattern for any transaction. Also, it try to reduce irrelevant information. It sorts the items in a descending manner. And as we know, this descending sort means to find frequent occurrence firstly, because items with higher probability or higher frequency are presented firstly, and at the end just items with minimum value of support are presented. So items in the top of the list have more chance of occurrence. And as I know, the result is not larger than the original database. It's a simple and fast. Okay. That is enough for today. Thank you for joining the class. You can go to exam to do your exam. Okay. Is there any question? Don't worry about the exam. It's simple. And it has only half of a score. It says a score is half of marks. So don't be worried about the exam. Just it has half of marks. Totally in this course you have 20 marks. This quiz just has half of scores. So don't worry. Be calm and just simply do your best. Okay, have a good day, and I wish